Okay, folks, here we go. Apologies for having to get this via video, but best I could do in this situation. We're going to do lesson 3 and then a separate video for lesson 4. I'll assign questions. I'll assign questions after that. So here we go. So lesson 3. So we've been talking about scale factor, and we've specifically been looking at linear and perimeter scale factor. Now we're going to look at the comparison between linear scale factor and area. Okay. So just like our other charts before, we're going to look at a similar chart, and hopefully by the end of the chart, you have a good idea of how linear scale factor relates to area and area scale factor. So as before, if we have our figure, let's say it measures 3 by 5. So we have some kind of rectangle, measures 3 by 5. The area of that rectangle, remember that area is equal to length times width. Okay, length times width. So 3 times 5 is our 15. If we apply a linear scale factor to these dimensions, our 3 by 5 dimensions, if we apply a 2-to-1 ratio scale factor, or 2, because that's what it reduces to 6 by 5, 3 times 2 gives us 6, 10 times 2 gives us 10. That gives us our new length and new width. So our new length and new width of our figure is 6 by 10. And then again, if we calculate the area of our new figure, length times width, 6 times 10 is 60. Now we're going to look at the comparison between our new area over our original area. Okay, so that's our scale factor, right? Scale factor, new over original. So our new area was 60. Our original area was 15. That reduces, they both divide by 15 to 4 over 1, or just 4. Okay, so eventually we're going to look at the relationship between this number, 4, to this number, 2. And as we work through this, I want you to see if you can come up with some kind of relationship. I have mentioned it in class before, so maybe you're able to figure that out right now. Let's look at example B. Our original figure, our figure we start out with is 9 by 6. So it measures 9 by 6. So this is 6, this is 9. Our original area is length times width, 6 times 9, or 54. Okay. If we apply a 1-to-3 ratio, this is a reduction by 3, a factor of 3. If we apply our 1-to-3 ratio, okay, over here, somewhere we're doing the math, we're going scale factor is equal to drawing over actual, or my 1/3 scale factor is equal to x over my original. If we do 9 and we cross multiply divide, 9 times 1 divide by 3, we get 3. We do a similar process for the 6. 1 over 3 is equal to x over 6. 6 times 1 divided by 3, we get 2. So our new dimensions of our figure are 2 by 3. Well, actually, I should write 3 by 2 because we did length first. 3 by 2. That means our new area, which is still length times width, 3 times 2, or 6. Now we're going to compare our new area of 6 to our old area of 54. And we reduce that fraction. 6 over 4, both reduced by 2. I'm going to divide by 2. That's going to give me 3 over 27. And both 3 and 27 divide by 3. So I'm going to divide by 3. That's going to give me 1 over 9. And again, eventually we're going to look at the comparison between this value and this value. Okay, let's do C. We'll do C and D and then see if we can figure out what that relationship is. So C, our original figure is 4 by 8, which means our original area is 4 times 8, or 32. And then somewhere we're going to apply a 3-to-2 ratio, or 3 over 2 as a fraction. And then you should ask yourself, well, is this going to be an enlargement or a reduction? Hopefully in your mind, you're saying enlargement because the 3 is bigger than the 2. So somewhere on scrap paper, I'm going to erase this. I don't want it in the way. Somewhere on scrap paper, I'm going to do those calculations, use my scale factor as drawing over actual. My scale factor was 3/2. And let's convert the 4 first, something x over 4. 4 times 3 divided by 2 is 12 divided by 2, which is 6. So my new width in this case is 6. And my new length, I do the same with 8. 3/2, my scale factor, x over 8. 8 times 3 divided by 2 is 24/2, 12. 6 by 12, which gives me a new area of 72. Now I do a comparison, my old area over my new area over my old area, 72 over 32. And then I start to reduce that. Maybe you see it divides by 2, 36 over 16. Well, that divides by 2 again. That gives me 6 over 8. No, it's not 6, sorry. 36 by 2 is not 6. 36 by 2 is 18. And then that divides by 2 to give me 9/4. I'm going to write that outside the line there. And again, we're going to look at this relationship between this number and this number. Maybe you see it already. We have let's change colors here. 2 is our linear scale factor. This number is 4. 1/3 is our linear scale factor. This is 1/9. 3/2 is our scale factor. This is 9/4. Maybe you can predict, if we're looking at our linear scale factor, what this number will be. Okay, so let's go through that work. 3 by 12 is our original dimensions. 3 times 12 is our area. 3 times 12, that's 36. If I apply a 2 to 3 scale factor, which is going to be a reduction to 3 and 12, this is what it looks like. My scale factor formula, always the same. I'm going to apply it to the 3 first. What did we say? It was 2/3? 2/3 is my scale factor. 2/3 is equal to x over 3. 3 times 2 is 6, divided by 3 is 2. And then I convert my 12. 2/3 is x over 12. 12 times 2 divided by 3 is 24, divided by 3 is 8. So my new dimensions are going to be 2 by 8. 2 by 8. Or my new area is 16. So my original area was 36. My new area is 16. So let's look at that. 36, new area is 16. 36 is my old. Both of those divide by 2. Gives me 8 over 18. Again, they divide by 2. That gives me 4 over 9. Reduced. And then maybe you were able to predict that that was actually going to be 4/9. Because if you see this, that's what we're going to be looking at compared to this. So that's the relationship we want to look at. We want to look at how those numbers, 2 for a linear scale factor, 4 for the area, 1/3 for the linear scale factor, 1/9 for the area scale factor, 3/2 linear, 9/4 area, 2/3 linear, 4/9 area. Hopefully, you were able to mentally come to the conclusion that the relationship between linear scale factor and area scale factor is that area scale factor is the linear scale factor squared, multiplied by itself. So if I have a linear scale factor of 6, my area scale factor is 6 squared, or 36. If I have a linear scale factor of 1 over 2, my area scale factor is 1 over 2 squared, which means 1 over 2 times 1 over 2, which is 1 over 4. So the relationship that we now know between linear scale factor and area scale factor is that if you square the linear scale factor, you will get the area scale factor. And you can work that backwards also. If I know that my area scale factor is 16, my linear scale factor is going to be the square root of 16, or 4. If my area scale factor is 9, my linear scale factor is the square root of 9, or 3. So both ways, you can go from one to the other. Hopefully you were able to see that relationship through that investigation. And now we get to apply that stuff. Example 1, Maggie has scanned an 8 by 10 photograph to her computer. Maggie would like to increase the size area by 44%. Determine the area scale factor and then the linear scale factor. Okay, so the area scale factor, ASF, area scale factor, is going to be 100% plus the 44%, or 144%, or as a decimal, 1.44. And remember, to go from area scale factor to linear scale factor, you square root. So that's my area scale factor. To get my linear scale factor, I take the square root of 1.44, which gives me 1.2. And you can try that on your calculator to test it. Question B, explain why the scale factors are different. Well, remember, if this is my figure, linear scale factor is just this dimension. Actually, I'll change colors. Is just a dimension, a length or a width, or really even a perimeter if I wanted to, right? We talked about that many times. Our area scale factor, oops, that's the wrong blue. We're still talking about the same figure, except area is all of this space, all of this space. Okay. So they have to be different numbers. We're talking about different dimensions. So now in linear scale factor and perimeter scale factor, we're just dealing with that length dimension, whether it's a perimeter or an individual length. Area is the space occupied. Okay, so the numbers have to be different. Question C, determine the dimensions of the enlarged photograph. Now that we have a linear scale factor, we can apply that linear scale factor and get our new dimensions. And we do that just like we have been. Scale factor is equal to drawing over actual. And remember, we have 2 dimensions. We have to do 2 calculations. Our scale is 1.2 to 1, just make it a fraction, is equal to x over my 8. Well, 8 times 1.2 divided by 1, that gives me 9.6. I do the same for my 10 inches. 1.2 to 1 is my scale factor, is equal to x over 10. 10 times 1.2 divided by 1 gives me 12. And these are inches. Yes, inches, the double hash mark. Okay, so the same manipulation of scale that we've been using. Question D. Question D is going to help us see that relationship. The enlarged photograph will be printed at a digital print shop on a color printer. Assuming the white areas of the photograph we'll also use ink. Calculate the area the printer must cover by the following 2 methods. 1, using the dimensions of the enlargement. So we just basically use the area formula with our new dimensions, which were 9.6 times 1.2, or sorry, not 1.2, 12. 9.6 times 12, 115.2 inches squared. It's area, so we have to square our units. And then the other way, using the original area and the area scale factor. So our original area was 8 by 10 or 80. And if we apply our area scale factor, just like we do before, drawing over original or actual, my area scale factor was 1.44 over 1 is equal to, what am I going to get when I convert 80? 80 times 1.44 divided by 1, 115.2 inches squared. So we've touched on this type of calculation before. We talked about it the other day. Another way to use those scale factor scale factor values. This is the way that we have been doing it. Convert the dimensions, then calculate what you need to. Either or, perfectly fine. Okay, over the page. Question E. Maggie must also produce a print whose area will be reduced by 25%. Reduced by 25%. If it's reduced by 25%, that's 100 minus 25. That means it's 75% of the original. Okay. That would be our area scale factor. Determine the dimensions of the print to the nearest hundredth of an inch. So if this 75% is our area scale factor, then our linear scale factor is the square root of 75%, which is actually 0.75, because we need that as a decimal. Let me write that a bit better, 0.75. That's our linear scale factor, and then we convert our dimensions. Linear scale factor is drawing over actual. We're going to convert our 8 by 10 original. So I go square root of 75 over 1 is equal to, what am I going to get when I convert 8? And I do the same calculation for my dimension of 10. Cross multiply divide in your fancy calculators, 6.93 inches and 8.66. Oops, that's a bad 6. 8.66 inches. New dimensions. That was question 1. Question 2. Marco, owner of Map It Incorporated, has produced a map of Canada with his employees. The area of the province of Alberta is approximately 661,850 kilometers square. On Marco's map, the area of Alberta is represented as 264.74 centimeters squared. The scale of the map, linear scale factor, can be written in the form of 1 to something, 1 to x. Calculate the value of x to the nearest whole number. So we know that scale factor is equal to drawing over actual. So we know that the drawing 264.74 centimeters squared over my 661,850 kilometers squared is our scale factor, except that it wants it in this form, this ratio form. And remember, this ratio form, these have to be in the same units. Has to be in the same units. Okay, so before I get there, I can do this calculation. I can do this division and reduce these numbers. If I take my 661,850 and reduce it by 264.74, I get something approximately 1 centimeter squared over 2,500 kilometers squared. Divide both the top and bottom by that 264.74. That gives me a nice conversion. Now I just need to convert these kilometers to centimeters. Okay, so 2,500 kilometers squared is our area scale factor. To find our linear scale factor, I take the square root of 2,500. That gives me 50 kilometers. Now I convert that 50 kilometers to centimeters. Well, in every kilometer, there are 1,000 meters. And in every meter, there are 100 centimeters. Okay. And when I multiply that out, I get, what is that, 5 million? 5 million centimeters. So the scale on the map is 1 to 5 million. So that's what X is. The conversions from kilometers to centimeters and some of the bigger ones, kilograms to grams, things like that are a little bit tricky. If we need to, we can spend a bit of time in class going over how to do those conversions. Question B, on the same map, the area of the province of British Columbia is represented as 376.839 centimeters squared. Determine the actual area. So if I know my area scale factor was 1 centimeter squared over 2,500 kilometers squared, then I can do a drawing over actual, or a proportion, 376.839 centimeters squared over X to figure out the area of British Columbia. Do my cross multiply divide, works out to 942,097.5 kilometers squared, approximately. And it says, say, round to the nearest 100. Nearest 100, that's this place. This 9 is going to make that 0, 1, 942,100 kilometers squared. Okay, that takes us to the end of lesson 3. Some questions will be assigned, and again, this will be covered on, it'll be also covered on a hand-in assignment coming later.